It's moving. Wow. Worms are awesome.
Ooh. Oh my god.
It's stretched.
Pen 5.
Now it feels comfortable.
Yeah.
6. Cornell, fake ID.
And they regenerate. Like crazy.
Yeah. Wait, what, Dartmouth, what?
Oh.
Awesome. Okay, so we have a low bubble, no worries. And then you can put it here, just don't go to the bottom. So yeah, right there is fine. Awesome, awesome. Perfect. Great. Okay, yeah. This resin is typically better for specific compounds, right? And so what we basically know from structure is that this it prefers more of a basically aqueous, some more water, higher percent water than this one does. And so we can exploit that difference by changing our solvents. But it has to do with the essentially structure of the compounds and how they interact. Yeah. Of course.
So we could go to Fahrenheit. So what do you think is going to happen if I drop this into this water?
Should I put it in?
Yeah. So this is really cold, and this water is at room temperature.
Nice.
Yeah.
Split back into the gas.
And so now,
Do you want to just slow down?
they're blowing up. Now I'm going to add a film of soap on the top of this flask.
So I was trying to see if I needed
So I can try.
like pump coating.
There we go. And now we're capturing that carbon dioxide that we've produced and this cloudy gas. So you can pop it whenever you want.
Thank you. I'll see when it gets bigger.
Okay. Cool. So this cloudy gas that's in there is actually water vapor from the air around us. And so because this carbon dioxide gas is so cold, it's partially condensing the water vapor in the air so that now we can see it and it looks like a crystal ball on top of our flask.
So when I pop it, what will happen?
Let's find out. There you go. So did you see how that gas sunk down around our flask? So that's because this cooled water vapor is colder than the air around us. So it's denser, and so when it encounters the air around us, it's going to sink down along our flask. Good job. You got some really good questions.
That when we lower its temperature below a critical temperature, the electrons in it can flow without any sort of resistance. And this means that the circulating electrons are going to generate a magnetic field, which is going to repel the magnetic field from this magnet here. And as a result, it kind of floats above the material as a result of the force generated from the magnetic field lines upon the
Then it comes.
sort of see it by spin it.
So what do you think is going to happen if I drop this dry ice into this flask?
Yeah, now it's getting a little bit too warm.
Let's test it.
And so you can see that
So now we can see here that
it's
the
not
dry
expelling the
ice
magnetic
is
field lines as much because now it's above its critical
back
temperature.
into a gas.
And so the electrons are experiencing resistance to flow.
So this
Those
is a
currents are
process called
decaying.
sublimation.
And
Where
so,
material goes through a different.
superconductivity is something that's only observed at very, very low temperatures. When these very, very so electrons are generally like the same, so they're the same charge dioxide, but they cancel each other out, right? right? They don't want to interact. However, there are very, very small attractive forces that if you lose all the other energy from the system, i.e. you're at really low temperature, these attractive forces are enough to allow the electrons to pair together.
Yeah,
And when they're paired together, they can form this condensate, which is like a different sort of state, and it can have different properties. And one result of this condensed state
And that's a process
is
called
that
sublimation. So now what I'm going to do is I'm going to put some soapy water along the top of this.
yeah. So this is
And
something
now
that we
we're
refer to
capturing
as a
that
phase
carbon
transition.
dioxide that we're
Phase
sublimating.
transition.
And if
So
you
it's not
want,
like a chemical reaction, because it's not like chemicals interacting and changing their chemical composition, but it is a structural change in the material, sort of. Or it's an abrupt change in the material's properties. So, yeah.
Yeah, we have a super.
This type of light to tell us something about a material, okay? And so what I have here, it's just a regular LED, right? But I'm gonna put a filter on top of it. It means that, okay, I'm blocking some of the light, but what I'm doing with this filter that's pretty special is that light, which has many different directions, you know, you think of light as a wave, but the wave can go, could be this way, could be this way, could go this way, could be any direction. What this filter is doing, it picks one, right? And it's only letting that light through. And I have a second filter, and so what I would like you to do is to put the second filter on top of it. Good. So what do you see? Anything different? No, right? It looks about the same.
Yeah, but
Now
a little more.
Okay, good. You lose a little bit of light. Okay, now I want you to lift the second filter and rotate it. All right, what do you see? It went down. So what we did,
Oh, because he's changed the
we blocked the light, so we picked a direction, right? And originally, when the two filters were in the same direction, the light that went through the first one got through the second one. But then I turned, exactly. So now I blocked the light. I've turned off the light, right? Okay. So this means there is no light coming to your eye. But what's amazing is that there's some materials that when you put them between these two filters that are crossed, it changes the direction of the light so that it actually goes through the second filter and you can see it with your eyes.
even though it's opposite.
Yeah, which is why it's amazing. So let's give this a try. So lift the filter for me. And so I'm going to show you two materials. This is regular glass quartz, and this is a crystal of calcium carbonate, calcite. Okay? So I'm going to put calcite and glass, and I want you to look at it with your, do you see a difference between the two?
Yes, this is more.
Yeah, one is bright and
The
one
light
is
is
dark.
going through this one.
Yeah, it almost looks like it glows, right? Which is so weird. Yeah. But what calcite is doing is, if you heard about the term refraction, it takes, yeah. So
No, this pencil thing.
yeah, exactly. It's the pencil thing, exactly. And so calcite does something that's called double refraction. So it changes the direction of the light, so it actually comes through the second filter, right? And there are many materials, some of which you find in nature. So calcite is one, because that you find. Mica is a silicate. This is another material that does the same thing. And so it's not transparent, but what's cool about mica is that you can flake it off. And so I have a flake.
You just did the half.
A flake of mica, and let's look at it. What do you see?
Oh, all different colors.
Yeah, that's even cooler because not only did it change the orientation of white light,
But it separated in
it separated it into the different wavelengths. So now you see color, right? Okay, so everything that I'm showing you right now, these are crystals, okay? This is a plastic fork, okay? Not a crystal, right? It's made of a polymer, polystyrene, but go ahead and put the plastic fork between. Go ahead. What do you see?
the same thing. All the colors.
Yeah. Does it look colorful?
Yes, it does.
Yeah. So what is happening? So the way we think about this, so polystyrene has these long chains, right? And these are polymers. Normally, it's like a pot of spaghetti or noodles. It's all sorts of different directions. But because of the way they made the plastic form, they had to mold it and extrude it. All of the chains, the noodles, had to be forced in a particular direction, and you're actually seeing how the material got stressed as it was being formed, okay? And so there are areas of high stress and low stress that you're seeing with different colors. And so I might ask you to do an experiment for me. So what we're gonna do is to take a piece of plastic, this one should work, and you're gonna stress it out for me under the cross polarizers. So go ahead and pull. What do you see as you're pulling? Yeah, you should be able to see different colors, and the colors are gonna intensify in certain areas. Good. Right. Okay, and so this becomes important. You are mechanically changing the structure at the molecular level, which is, you're strong, right? But you're taking all of these polymers that are, randomly oriented, and you're picking a direction, and they're being pulled. Not all of them are going in the exact same direction, and they're not all aligned the same way, so you're seeing different colors, right? And so what an engineer can do with a technique like this is that if where it's likely to break, and if you pull, actually I can see it, it's right here. There's a region here that looks like that is where it's going to fail. And so, you can pull it.
Oh.
There we go. All over. There she goes.
So do you think there might be a lot of termites in the ink factory?
I think mostly, oh yeah, so I think these I just grabbed like next door, like literally outside, so hopefully we don't have them too many on campus other than that, but pretty much, oh, you know what, I think this is the female that has eggs, so she doesn't want to move, so I'm going to put her back, because she's just super pregnant, so she doesn't want to play our games. She's like, no thank you, please leave me be.
We can celebrate her baby shower.
Yeah, that's right. Okay, we'll try that one. Did you want to try and draw something and see if the termites will follow? So only blue ink works. Do you want to try and draw something and have the termite follow? I'm going to move this too because I want them to get too warm. Actually, I should put these are isopods. Yeah.
Isopods are also attractive.
What's that?
Do isopods also like me?
They don't, but the reason the isopods are here, we keep these as like class pets, and the students do observations with them. But isopods and termites do the same kind of function. They break down decaying matter, so dead plant matter.
10 minutes, we'll be transitioning buildings. At 10 minutes, Orange will be changing buildings.
He's not good.
What do we see? Where is the graph higher? Can you see this? Yep. So if we look at this little hint right here,
What's closer to this side of the group?
Fuzzy?
Yeah.
Is it?
Not quite. What made you say 12?
And it curves it such that if another object, like a planet, goes near it, its trajectory, the way it moves will actually get bent. Oh, sorry. Oh, good catch. You want to give it a try? Nice, yeah. So by bending this very big object, like the sun, it bends space and time such that a smaller object like the Earth is going to get attracted to it. Does that make sense?
And that even happens to light rays. So light rays will also be bent. So just like what we did before and this went off. So if this wasn't here, light rays will travel in straight lines. But if this is here, now light rays are going to feel the curvature and they're going to be bent a little bit.
But that only happens